So we're going to talk about a set of procedures for weighing the strength of statistical evidence. And what we're going to be trying to do is determining whether or not two qualitative or categorical quantities are independent based on information that's given to us in a contingency table. Now, this information is what we're going to call observed frequencies. And this information, this set of data will either be given to you, or if you choose to do your project on this, then it's data that you're going to be finding yourselves and organizing into a contingency table. A contingency table is simply just a two-way table. So let's say, for example, I'm a math teacher and I'm female. So I'm a female math teacher. If I were to do a study on gender and let's say level of teaching, are you more likely to find a math teacher at a high school level than at an elementary school level? I could separate my data into math teachers level of teaching. So like I would qualify for high school instead of elementary school or middle school. And I would be female versus a male. Okay, so that's basically how this two-way table works. We basically have these two different categories. So chi-square hypothesis testing is a test, and it is used to determine whether there is in fact a significant difference between what are called expected frequencies and these observed frequencies. The first thing we have to do from the very beginning is identify what's called the null hypothesis. The null hypothesis, the symbol is H naught, tells me that variable 1 and variable 2 are independent. So let's say that in your educational career, back to the example about math teachers and level of schooling, you think, okay, there's a lot of female teachers in my primary school and elementary school. And then as I got to high school, I see that there are more male math teachers in high school. So you want to conduct a chi-square hypothesis test to determine whether there is significant evidence towards this hypothesis. So your null hypothesis is no, there's nothing going on. I am just as likely to have a male math teacher in elementary school as I am to have them in high school. So that's basically what the null hypothesis says. Now, the alternative hypothesis, which can either be H1 or HA, is the reason why you conduct a test in the first place. And that is because I have noticed that perhaps there are more male math high school teachers than there were in elementary school. So that's going to tell me that variable 1 and variable 2 are not independent, or some people say are dependent. So in my example of gender and level of teaching for math teachers, my null hypothesis could be gender and level of teaching are independent, and the alternative hypothesis would be gender and level of teaching are not independent. So something as simple as that. So the next step for us to be able to conduct this chi-square hypothesis testing is to collect our data and create a contingency table. So right now there's a lot of debate about whether or not students should return back to the classroom. So let's say that you have noticed that your parents' friends, a lot of those who have elementary school aged children, are opting to send their kids to school face to face. And it might be because of the fact that they have to go to work and they really don't have anybody to watch their kids because they're younger, or perhaps they have found that being their teacher and parent is a lot of work and it's very frustrating for them because they're little kids. Versus, let's say you've noticed that some of your friends, your parents' friends who have high school or secondary age children, that they are more likely to say yes, they can go ahead and stay at home, whatever the reasons may be. So chi-square hypothesis testing doesn't tell me any reasons behind any of this. We just want to find out, is there enough statistical evidence in favor of one hypothesis over the other? So right now I have collected my data and I basically have what's called a 3x3 contingency table. It's called 3x3 because eventually when we put this into the calculator, we're going to put this in a matrix. and rows go left to right and columns go up and down. So right now this is considered a 3x3 matrix, so I have a 3x3 contingency table. So notice that here we have parents with kids in elementary school, parents with kids in middle school, parents with kids in high school. So we're going to have to figure out a way to call that category. And then we have how they feel about going back to school. We have those that are in favor of returning to face-to-face schooling. We have those that are against it and those that are undecided. And these right here, these numbers would be collected based on a survey that you would conduct. So let's go ahead and label this the schooling age of children, just for the sake of calling that variable something, and preference of children returning to school. So the first thing you always have to do in a chi-square hypothesis test is identify your null hypothesis and your alternative hypothesis. So your null hypothesis is going to say schooling age of children and preference of children returning to school are independent. And the alternative hypothesis would say schooling age of children and preference of children returning to school are not independent. You could also write are dependent. So once we have established our null hypothesis and our alternative hypothesis, we're going to do a series of calculations. The first calculation that we have to do is to find what's called our expected frequencies. Now, the expected frequencies is based on probability theory. If in fact these two variables are independent, I should be able to find the likelihood of like how many people I would expect to be in each category by multiplying the two values together. Okay, so the formula to find the expected frequencies is row total times column total divided by the grand total. So we take our contingency table and we're going to add row total and column total and then the grand total. So the grand total means that we have interviewed 445 people for this study. How many parents with kids in elementary school are part of my study? 160 of them. How did I get 160? 100 added to 36 plus 24 is 160. How many parents with kids in middle school are part of my study? 70 plus 40 plus 10, 120. And how many are parents of high school students? 90 plus 50 plus 25, which is 165. How many of my 445 parents have said yes, they're in favor of returning to school? 260. How many are against? 126. And how many are undecided? 59. All I did was figure out the column totals and the row totals. Okay, so once I set up my contingency table, I can now actually start to find the expected frequencies. I work with each cell at a time. Each one of these values in this table is called a cell. Let's take a look at the parents with elementary school children who are in favor of returning to school. 100 of them in real time, like 100 of them who answered to my survey said that yes, they are in favor of sending their kids to school. To figure out the expected frequency, I'm going to multiply, according to the formula, the row total times column total divided by grand total. So for this cell, my row total is 160, my column total is 260, and of course the grand total is 445. So here I'm going to show my work. It's 160 times 260 divided by 445, so it's 93.483. I do the same thing for each cell. So for example, for those who are parents of elementary school children who are against, I would multiply 160 times 126 divided by 445, and that goes right here. If I want to figure out for undecided what is the expected frequency, I would have to take its row total times column total divided by the grand total. So 160 times 59 divided by 445. And I do that for every single one until I figure out my answers. So go ahead and take some time to figure those out. Put them into your calculator, multiply, divide. You can pause the video right here until you're done, and then you can check your answers. Okay, so this is what you should have gotten for your expected frequencies. Okay, so we found each one of these numbers by multiplying row total times column total divided by the grand total. So now we have not only our null hypothesis, alternative hypothesis, we have our contingency table of the observed frequencies, which is data that's either going to be given to you in the problem, or right now it's data that we have collected through a survey. And I was able to calculate based on the formula, row total times column total divided by grand total, I figured out the expected frequencies. So I have two sets of data. I have the observed, which are the actual results that I got from when I conducted the survey, and I have the expected, which is based on probability theory, if in fact these two are independent variables. So what do I have to do now? Now I'm going to find two other values. They are called chi-square calculated and chi-squared critical. The chi-square calculated value, just like its name suggests, is something we are going to have to calculate. Now there is a formula. Here is chi-squared. It is the sum of the difference between the observed frequencies and the expected frequencies squared divided by the expected frequencies. So I like to call this pho and phi just for the sake of helping you remember the order in which we're going to do this. So we're going to set up a chart. This chart I actually did using the graphing calculator. You can do this on Excel as well, or you can do this by hand. But I will show you again in another video for the graphing calculator how you can actually put this into your calculator. So I'm going to call this pho, phi, pho minus phi, pho minus phi squared, pho minus phi squared divided by phi. Again, say it with me. Pho, phi, pho minus phi, pho minus phi squared, pho minus phi squared divided by phi. So this means the observed frequencies, the expected frequencies, observed minus expected. I'm going to square those values, and then I'm going to divide by the expected frequencies. When you look at your table, it doesn't matter which way you put it in the calculator. I went across. So I went 136.24, 136.24. And if I do it in that order, I have to be consistent and also put in my expected frequencies in that same exact order. 93.484, 45.303, 21.213. So notice it's exactly in that same order because you want to compare apples to apples, okay? So now I find the differences, I square those differences, I divide by the expected frequencies, and at the end, this is sigma. Sigma tells me I have to find the sum. So I'm going to find the sum of my last column, and I get 7.0956. So that 7.0956 is what is called the chi-squared calculated value. So now I have to find another value, which is called the chi-squared critical value. But in order for me to find this chi-squared critical value, there's a few more things that I need. The first thing I'm going to have to determine is what's called the degrees of freedom. The degrees of freedom is the number of ways that we can rearrange the numbers in the table. This Greek letter right here, lowercase v, is nu, and it's basically just degrees of freedom. In the calculator, it will give you df, so that's why I just wrote df for you there. And to figure out degrees of freedom, the formula is to take the number of rows minus 1 and multiply it by the number of columns minus 1. So we already talked about how in this example, we have a 3x3 matrix. There are 3 rows. Remember, rows go left to right, and we have 3 columns. So that goes up and down. So here, the degrees of freedom is equal to 3 minus 1 times 3 minus 1, which is 2 times 2, or 4. So the degrees of freedom in this problem is 4. The other thing we have to talk about is what's called the significance level. The significance level is the likelihood the results of the study might fall in the rejection region under the curve. Think of this as what is the chance we're willing to accept that we're actually wrong, that what we're saying to be true is actually not true. So most of the time, it's going to be given to you on examinations, whether they want you to conduct this at a 1%, 5%, or 10% significance level. And if you're thinking to yourself, where do they get the 1%, 5%, 10%? Do people just kind of come up with it? Yes, they did. Okay, that statisticians actually kind of just came up with the 1%, 5%, 10% as the chance they're willing to take that they're wrong. So most of our problems are conducted at a 5% significance level. When you go ahead, if you choose to do hypothesis testing for your project for this course, then you might want to also do 5%, and your reasoning could be just because it is the most commonly used level of significance. So what do I do with these two values that I found, the degrees of freedom and the significance level? When I go to find the chi-square critical value, there's an actual chart. Now, the chart is going to have me match the significance level with the number of degrees of freedom. So here, remember that V, that nu, tells me the degrees of freedom, which is 4. So I'm going to match 4 with 0.95. And you're like, why 0.95 if we're talking about 5%? So different tables that we use in statistics are shaded differently. In the particular table that I have for you right here, what's shaded is everything in the left. So the cutoff right here, where the critical value is, where you see that C, that little C, that is actually here 5%. This is the rejection region. This is the area that we're willing to say that we are actually wrong, and this is where we're going to reject it. So because this particular graph has this shaded on the left, then in talking about a 5% significance level, we actually are going to look under the 95% mark, because what's shaded here is 95%. I'm sorry, this is a little confusing, but just realize what's shaded here is most of it. So the cutoff is 5%, so this indicates 95%. If the cutoff is 1%, you would look under 0.99. If the cutoff is 10%, you would look under 0.90, 0.9. For right now, we're going to look under 0.95. We're going to match it to our 4 degrees of freedom. And so our chi-square critical value is 9.488. So 9.488 is going to be our critical value. Okay, so now we are ready to make a conclusion. I know it seems like a lot of calculations. The first thing we did, if you remember, was talk about the null hypothesis, saying that the two variables are independent. We talked about the alternative hypothesis, saying that they are not independent. We went ahead and organized our data into a contingency table. Those were the observed frequencies. We calculated the expected frequencies by doing row total times column total divided by grand total. Then we went ahead and found what's called the chi-square calculated value, phi minus phi squared, minus phi squared divided by phi, and I took the sum, and that's my chi-square calculated value. The chi-square critical value comes from the chart. I had to figure out the degrees of freedom, number of rows minus 1 times number of columns minus 1, and then at a 5% significance level, I looked under 0.95 in the chart. So I have these two values. I am ready to make a conclusion. So I'm going to compare them. Since my chi-square calculated value of 7.0956 is less than my critical value of 9.488, I am going to accept the null hypothesis, and I'm going to conclude that schooling age of children and preference of children returning to school are independent, which tells me that it doesn't matter whether the parent has an elementary school age child or a middle school age child or a high school age child. It really has nothing to do with their decision on whether they are in favor, against, or have no opinion or are undecided about whether or not students should return back to the classroom. Okay, so there's not enough statistical evidence to suggest that there is something going on here with this decision. So I want to go back to show you how here 9.488 is the chi-square critical value, because my calculated value was 7 point something, which is a number smaller, like on a regular number line, it's smaller than 9.488. It falls in the shaded region, which is the acceptance region. Had my chi-square calculated value instead of 7 would have been, let's say, 17.09 compared to 9.488, it would have been out here in the rejection region. So that's when I would have rejected the null hypothesis. And if this said reject the null hypothesis, we would conclude that schooling age of children and preference of children returning to school are not independent. Okay, and here it would have said 17.0956 is greater than the critical value. But this is kind of cookie cutter. It's almost like a verbatim type thing that you just memorize so that you can put it into your answer. So this is basically a little bit of a breakdown or recap of all the stuff we've done for hypothesis testing. Number one, like I said, you have to identify the null hypothesis that says variable 1 and variable 2 are independent. The alternative hypothesis is next, and it says variable 1 and variable 2 are not independent. Your significance level will either be 1%, 5%, or 10%. If they don't give you one, just go ahead and use 5%. The observed frequencies usually are always given to you in a contingency two-way table, or in our case, we did a survey and we got the values for the observed frequencies. The expected frequencies are based on probability theory, and you're going to have to calculate them using the formula row total times column total divided by grand total. The degrees of freedom is the number of ways to rearrange the data, which is the number of rows which go left to right minus 1 times the number of columns which go up and down minus 1. Then we're going to find the chi-square calculated value by going phi minus phi squared, phi minus phi squared divided by phi. We get the sum of that column, and we're going to find the chi-square critical value from reading the chart under 0.95 because it is a 5% significance level, and in our case, it was 4 degrees of freedom for our example. And the conclusion, since the chi-square calculated value is less than the chi-square critical value, we accepted the null hypothesis and conclude that it is independent. Have we said greater than, then you would have said we reject the null hypothesis and conclude that they are not independent. And that's it for chi-square.